Imagine you want a robot to unload a box from a truck, carry it through a doorway, place it on a shelf, and then plug in a charging cable. The strange part is not that a robot can do one of those things. Factories have used robots for decades. The strange part is asking one machine to move through a world designed for human bodies, then use human tools, without rebuilding the whole world around it. That is the core question behind humanoid robots. Why build robots in our shape at all? Why give them legs, arms, hands, a torso, and something like a head, when wheels are simpler and robot arms can already be very precise? The short answer is that our world is full of human-shaped assumptions. Door handles sit at hand height, stairs are made for feet, shelves, carts, light switches, tools, ladders, kitchens, factories, and warehouses are arranged around the reach, balance, and size of people. A humanoid robot is not just trying to look familiar, it is trying to fit into an environment that already exists. But this is also where the biggest misunderstanding begins. A humanoid robot is not automatically more advanced because it looks like a person. In many jobs, a wheeled robot, a conveyor belt, or a fixed robot arm is cheaper, stronger, safer, and easier to control. The human shape is not magic. It is a trade-off. To understand that trade-off, split the problem into two halves. One half is mobility, which means getting around. The other half is manipulation, which means doing useful work with objects. Mobility sounds simple until the floor becomes messy. Wheels are excellent on smooth surfaces. That is why delivery robots, warehouse robots, and cleaning robots often use wheels. Wheels are energy efficient, mechanically simple, and easy to control. But wheels struggle when the environment has stairs, clutter, narrow gaps, ladders, or uneven ground. Legs are harder, but they can step over things. They can place a foot on a stair, shift weight, and recover balance after a small push. A humanoid robot with legs is attempting to use the same pathways humans use, instead of demanding ramps, rails, or special lanes everywhere. Still, legs are expensive in every sense. They need powerful motors, fast control systems, strong joints, careful balance, and lots of energy. Walking is a controlled fall, repeated over and over. Every step requires the robot to predict where its weight will go, place a foot in time, and adjust when reality is slightly different from the plan. Humans make this look effortless because our bodies and nervous systems are deeply optimized for it. For a robot, even standing still can be an active task. Motors may need to make tiny corrections many times per second just to keep the machine upright. Now look at manipulation. This is where humanoid robots become especially interesting. A robot that only moves is not very useful unless it can also do something when it arrives. It has to grab, lift, push, pull, twist, insert, sort, carry, open, close, and sometimes recover from mistakes. A human hand is a very complicated tool. It can hold a heavy box, pick up a coin, turn a key, squeeze a bottle, guide a cable into a port, or feel when an object is slipping. A robot hand does not need to perfectly copy a human hand, but it must solve the same basic problem. It needs enough contact with the world to control objects that vary in shape, weight, texture, and position. If you enjoy clear explanations like this, consider subscribing. The goal here is to make new technology feel less mysterious, not by hyping it up, but by taking apart the mechanism piece by piece. The reason humanoid robots are hard is that mobility and manipulation are connected. If a robot reaches for a heavy box, its balance changes. If it lifts something with one arm, its center of mass shifts. If it pushes a cart, the cart pushes back. The robot is not just moving its hand, it is coordinating the whole body. This is why videos of humanoid robots can look both amazing and awkward. A robot may perform a backflip in a lab, but struggle with a loose plastic bag. That does not mean the backflip is fake or useless. It means the skills are different. Dynamic movement is about controlling the robot's own body. Everyday chores are about controlling a messy world that does not follow a clean script. A box in a warehouse may be dented, taped badly, half open, heavier on one side, or placed at a strange angle. A shirt is soft and constantly changes shape. A cable bends. A door may stick. A tool may be lying under other objects. These are ordinary problems for people, but they are difficult for machines because the robot must perceive the scene, decide what matters, plan an action, and correct itself when the action does not go perfectly. This brings us to the hidden mechanism behind modern humanoid robots. They are not only mechanical machines, they are sensing and control systems wrapped in a body. A typical humanoid robot uses cameras or other sensors to understand its surroundings. It may estimate depth, identify objects, track its own joints, measure forces, and monitor balance. Then, software turns goals into motion. The goal might be simple in human language, like pick up the tote, but the robot needs a much more detailed answer. Where should the feet go? Which hand should approach? How tightly should it grip? What path should the arm follow? What should happen if the object slips? Older automation often worked best when the world was highly controlled. The machine repeated the same movement in the same place, thousands of times. Humanoid robots are being built for less controlled places. That does not mean they can handle anything. It means they are designed for environments where some variation is expected. Artificial intelligence matters here because it helps robots deal with variation. A robot may learn from demonstrations, simulations, trial and error, or large collections of sensor data, but it still has a body, and the body has limits. AI can suggest an action, but motors, batteries, joints, friction, weight, and safety constraints decide whether that action is possible. This is a key point. A humanoid robot is not just a chatbot with legs. A chatbot can be wrong and still finish a sentence. A robot that is wrong can drop an object, block a hallway, pinch a cable, damage equipment, or fall over. Physical intelligence has consequences. That is why real humanoid robot progress often focuses on narrow tasks first: moving bins, carrying parts, inspecting equipment, handling tools in a defined area. These tasks may sound less exciting than a robot butler, but they are economically important because they happen over and over in places built for human workers. Task economics is the practical reason humanoid robots exist. If a company can redesign an entire factory around traditional automation, it often should. Specialized machines are usually faster and cheaper for one repeated job. But many workplaces are not one perfect assembly line. They are a mix of old buildings, changing products, human workflows, carts, shelves, stairs, and tasks that happen in bursts. A humanoid robot becomes attractive when changing the environment is more expensive than building a robot that can adapt to the environment. In other words, the robot is trying to be a universal adapter for human spaces. That does not mean every home will soon have one. Homes are actually among the hardest environments. They are cluttered, unpredictable, emotionally sensitive, and full of fragile objects, pets, children, clothing, dishes, and personal habits. A warehouse bin is much easier than a toddler's toy under a blanket. A factory aisle is much easier than a kitchen after dinner. Safety is another major constraint. A humanoid robot is a heavy-powered machine moving near people. It must avoid collisions, limit force, detect problems, and fail safely. The more general the robot becomes, the more possible failure cases it has to handle. A robot that works only inside a fenced industrial cell has a simpler safety problem than one that walks through a busy hallway. There is also the battery problem. Human bodies run on food and are remarkably efficient. Robots need electrical power for sensing, computing, motors, cooling, and communication. A humanoid that walks, balances, lifts, and thinks at the same time uses energy quickly. Battery size adds weight, and weight demands stronger motors, which need more energy. Engineers are constantly balancing power, runtime, strength, speed, and cost. So why keep pursuing humanoids if the challenges are so large? Because the payoff, if the trade-offs improve, is flexibility. A robot arm bolted to the floor is powerful, but it cannot walk to another room. A wheeled cart can move, but it may not climb stairs or use a drill. A humanoid design tries to combine movement and hands into one platform that can be taught many tasks over time. The important word is taught. We should be careful with the idea of general-purpose robots. General purpose does not mean the robot wakes up knowing every job. It means the same body might support many skills, if those skills are trained, tested, and deployed safely. A humanoid robot may one day have an app-like collection of abilities, but each ability still needs engineering behind it. Another misunderstanding is that a human-looking body requires a human-like mind. It does not. A humanoid robot does not need feelings, intentions, or consciousness to be useful. It needs perception, control, planning, learning, and reliability. The human shape is mainly about the physical interface with the world, not proof of inner experience. There is also a social side. People react differently to machines that look like them. A humanoid shape can make a robot easier to understand because we can predict where it might move or what it is reaching for. But it can also create false expectations. If a robot has a face or walks like a person, people may assume it understands more than it does. Good design has to manage that expectation. The future of humanoid robots will probably not arrive as one sudden moment. It will look more like slow expansion from controlled tasks into messier ones. First, robots handle specific work in structured spaces. Then they become more reliable around people. Then their hands improve. Then their software learns more categories of tasks. Each step matters, but each step is limited by physics, cost, safety, and usefulness. The best way to think about humanoid robots is not as metal humans. Think of them as machines built to negotiate with a human-shaped world. Their legs are an attempt to use our pathways. Their arms and hands are an attempt to use our objects. Their sensors and AI are an attempt to handle variation. Their business case depends on whether that flexibility is worth more than simpler automation. That is what makes them fascinating. They sit at the intersection of robotics, artificial intelligence, labor, design, and economics. A humanoid robot is not impressive because it resembles us in a photo. It is impressive when it can take a vague physical world, full of objects made for people, and do useful work without everything being perfectly arranged in advance. If you have a question about humanoid robots, or you want a deeper explainer on robot hands, robot vision, or how robots learn from simulation, leave a comment and suggest the next topic.